This chapter is all about circular motion. Today we're going to go over centripetal acceleration and centripetal force, which are both force and acceleration in a circle. And then we're going to talk about identifying the direction of centripetal force, because this is one that a lot of people get incorrect. Because, well, we'll talk about why. We'll get to it. We'll talk about why. So, to begin with centripetal acceleration, we have to just talk about circular motion in general. So, any object that is rotating around a single axis undergoes circular motion. So, that can be as obvious as a ball on the end of a string spinning in a circle, or as maybe not so obvious as a car turning a curve.
Okay.
While the car is not attached to an axis, it is moving about a single axis, not in a full circle, but in circular motion. Okay? So, comes in many shapes and sizes. The line about which the object rotates we call the axis of rotation. So the easiest way to picture an axis of rotation is on a Ferris wheel, right? There's the tube that goes like perpendicular to the wheel that's in the very center. That's the axis of rotation for the Ferris wheel. The line about which the Ferris wheel rotates. Objects that are moving in a circle can experience what we call tangential speed. How do we say tangential? I guess struggle with that word. I want to say tangential, but there's not an R in there. So tangential speed, it's like the line tangent from math. That's what we're talking about here. Because tangential speed is the speed of an object along an imaginary line that is drawn tangent to the circular path. So if that object were to move in a straight line along, like if you cut the rope and the rock goes flying off in a straight line, that would be the imaginary line we're talking about when we're talking about tangential speed.
Okay.
When you want to solve for tangential speed, all you have to do is take the circumference of the circle, right? And divide it by the time it takes to make one rotation around the circle. Because the circumference is the distance around the circle, and then the time it takes to do one rotation would be the time, so that would be your tangential speed.
Gotcha.
So we'll do a lab in a couple days where you will have to solve for tangential speed. When that tangential speed is constant, so when that speed is not changing, we would call that uniform circular motion. So when you hear me refer to motion as uniform circular motion, I'm talking about an object that's moving at a constant tangential speed around in a circle. So when we did the lab where we spun the stopper, when we got the stopper moving at a constant speed so that weight no longer rose or fell, that would have been uniform circular motion. Tangential speed will increase the further you get from the center of the circular path. So when you're closer to it, you will go slower, and when you're further from it, so as your radius increases, then your tangential speed should also increase. If the period of time over which you're completing this motion remains the same. Obviously, if the time goes up, then it's different. The way the book described this, and I thought this was a really great way of explaining it, is imagine two horses on a carousel, right? They're stuck side by side, which means they travel the full distance of the circle in the same amount of time. Mm-hmm. However, the one that is further from the center, the radius is bigger, therefore the circumference is bigger, therefore that horse is traveling further in the same amount of time, and thus its speed must be faster.
Gotcha. So just like on a racetrack, you want to be on the center, because then
you're traveling less distance.
Gotcha.
Yep.
Okay.
Yep. Absolutely. It's also why people tend to say if you get on those like swinging chairs, right, and you want to go the fastest, you want to be on the outside, mm-hmm. right?
Mm-hmm.
Even when an object is moving at a constant tangential speed, when they are moving in a circle, we know they are experiencing acceleration, because acceleration is a change in velocity, not a change in speed. Mm-hmm. And they are still changing direction constantly when they're moving in a circle. Therefore, even when they're experiencing uniform circular motion and they're moving at the same tangential speed the whole time, they are experiencing acceleration.
Gotcha.
Acceleration of this nature is called centripetal acceleration. And we use the formula acceleration centripetal is equal to velocity tangent squared divided by the radius of the circle. So I just put these points on here so you knew what they were. AC is centripetal acceleration, VT is tangential speed, and R is the radius of the circular path. Centripetal acceleration is always directed towards the center of the circle. And I'm going to demonstrate why using the graphic that's on your notes. Okay? If objects are made to move faster along an established circular path, then they will experience tangential acceleration, where the magnitude of their tangential velocity also increases. So they can experience centripetal acceleration, which is usually just from changing direction, and then they will experience tangential acceleration if you make them go faster.
Okay.
Does that make sense?
Mm-hmm.
Here's the graphic I was talking about to explain why centripetal acceleration is directed towards the center. Okay, so it's just showing you how we add these vectors. Okay, so observe. Here's our initial velocity, right, in this direction. And then here is our second velocity. If we add these graphically, look which direction the change in velocity goes. It's perpendicular to these guys towards the center of the circle.
Gotcha.
So that's why we say centripetal acceleration is directed towards the center of the circle.
Okay.
Here's our first example problem of the day.
Yay.
You're going to calculate the orbital radius of Earth if its tangential speed is 29.7 kilometers per second and its centripetal acceleration that is acting on the Earth that would be 5.9 times 10 to the negative third meters per second squared. So you can use that first formula that we got, plug in the values we know, and solve for what we do not. Yep, so what we do is we take and manipulate that original equation. We make RB by itself, because that's what we're trying to solve for. So we wind up with the equation R is equal to VT squared divided by acceleration centripetal, and then we can simply plug our numbers in, our 29,700, and then we want to, that's meters per second, and then we want to square that, and then divide that by our 5.9 times 10 to the negative 3, and you should come out with 1.5 times 10 to the 11th meters per second, or if you went ahead and converted it back into kilometers per second, it would be 1.5 times 10 to the 8th meters per second. And 2 sig figs is accurate because this second number here is in 2 significant figures, and since it's a division problem, we go to the smallest number of significant figures. Awesome sauce. Now let's talk about centripetal force. When objects move in a circular path, their inertia tends to maintain their motion in a straight line, which would be tangent to the circle. Which means in order for an object to actually move in a circle, you must have a constant force being applied to oppose that inertia. Otherwise, the object will move in a straight line. It will not curve.
Oh. Okay.
Which is why if you're spinning a rock above your head on a string and the string breaks, the rock no longer moves in a circle, right? Inertia always keeps objects moving in the same direction unless there's an unbalanced force,
Oh, in a straight. Okay. I was thinking like it's spinning and it just goes that way. But then I was like, no, it goes that way because that's a straight line because that's
Right.
just like we were looking at earlier. Gotcha.
Yep.
Brain caught up.
So, yes, consider a ball and a string swung in a circle over your head. The forces that are acting on the ball are the force of gravity and the force of the string. Gravity pulls downward on the ball. The string force has both a vertical component, which cancels the component of gravity, and a horizontal force, which is equal to the net force on the ball. So, string's gonna pull up and in, and so the upward force will cancel the downward force of gravity, keeping the ball from moving downward, and then the force of the string on the ball in is what keeps it moving in a circle instead of flying off in a straight line. The inward directed force that's toward the center of the circle is called centripetal force. Now, sometimes this is one force, like we see with the string on the ball, right? The string's force inward, that's the only force. Sometimes it's a combination of forces, but the net force towards the center of the circle is called centripetal force. Here is the string, here's the ball, right? Mm-hmm. Gravity pulls down on the ball. Okay. The string exerts a force upwards on the ball that's equal to the downward force of gravity, which is why it stays level. And it also exerts a force towards the center of the circle, which is why the ball doesn't just yippee out of here. Right? This force right here, this net force in, that's centripetal force.
Gotcha. Okay.
Sometimes it's one force, like the force of the string. Sometimes centripetal force is a combination of different forces keeping an object moving in a circle.
So like a car going around a roundabout?
Yes, in that case, the centripetal force might be a combination of the door pushing on your shoulder, your seatbelt pushing on you, and the friction between your pants and your seat. But all of those forces are keeping you traveling in the same path as the car and not flying off in a straight direction, in a straight line. And the net force of them all added together towards the center is the centripetal force.
Gotcha. Okay.
Okay. Newton's law can be used to find centripetal force, because we know that force is equal to mass times acceleration. So if you take the mass of the object and the centripetal acceleration, which we just learned how to calculate, we can find the centripetal force.
Gotcha.
If you want to combine that equation with the previous equation for centripetal acceleration and just make them all one thing, you'll get this equation, wherein we've just replaced centripetal acceleration variable with tangential velocity and radius. Oops. An example problem. A pilot is flying a small plane at 56.6 meters per second in a circular path. The radius of that circle is 188.5 meters. The centripetal force needed to maintain that circular motion is 1.89 times 10 to the 4 newtons. What is the plane's mass? So if we manipulate our equation to get mass by itself, what we wind up with is mass equal to the centripetal force times the radius divided by the tangential velocity squared, which means we're going to take 1.89 times 10 to the 4th. Can't really see the decimal place there. There we go. And we're going to take that times our 188.5 meters. And this would be newtons. and then divide all of that by our 56.6 meters per second, and then that obviously needs to be squared. And when you do that, you'll come out with 1,110 kilograms, which you could also write as 1.11 times 10 to the third kilograms. But it should have 3 significant figures because both this number and this number are in 3 significant figures. So when we go to the smallest number of significant figures, we have 3.
Mm-hmm. I've been learning significant figures and I've been so happy.
Yay! Okay, the last thing we should talk about a little bit is, I didn't realize I had this slide in here. We just talked about this, but centripetal force can be a push, it can be a pull, it can be a combination of forces, but it's always directed towards the center of the circle. So we talked about that, right? It's a net force, centripetal force is, so it can be a combination of things. Sometimes, when we're dealing with science, personal experience can confuse us. Okay? For example, a popular one is that children often believe that the phases of the moon are caused by the Earth's shadow on the moon, right? So like the Earth is passing in front of it. Mm-hmm. That's a common misconception that children have because they observe that the moon is a circle and the Earth is a circle, and they just sort of assume that's why we see those patterns. In fact, in real life, we see those patterns because of the portion of the lighted side of the moon that's facing us. Mm-hmm. But that's an example of how our life experience doesn't always mesh up with science.
But in a way, it's kind of right. In a way.
In a way.
It's only at one point that kind of causes that.
Yeah. And it's never the shadow of the Earth on the moon that's causing it, which is what a lot of kids think. Here's another example that has to do with circular motion. When you are on a merry-go-round, and you're being pushed crazy fast by the other children on the playground, and you're holding on for dear life, what does it feel like is happening to you? Yes, it feels as though you are getting pulled off. Mm-hmm. So for a long time, people called that centrifugal force. Mm-hmm. Yes. And it was believed to be a real thing. Okay? They thought there was a centripetal force and a centrifugal force. We now understand that that is not the case. Okay? What you are not feeling, you're not feeling a centrifugal force. Okay? There is no force. We drew the free body diagram, right, of the rock on the string. There's no force moving outward on that rock, away from the center of the circle. It doesn't exist. Instead, what people are feeling is their body's inertia. They are sensing their body's tendency to resist a change in motion.
Which is why we feel like we're going out.
Yes, because if you did let go,
you'd go out.
You would fly outward because your inertia is your body's tendency to resist changing its motion. And that is a change in speed, but also a change in direction. Your body resists changing direction unless a force acts on it. So unless the force of you holding on to the merry-go-round keeps you moving in a circular motion, your body would rather you continue in a straight line. And so what you feel is actually your inertia. You're feeling yourself not wanting to change your motion unless you have to. So, just something to remember about circular motion. You will sometimes still see the word centrifugal force thrown around online, in old textbooks, and now it's more of a, we use it to remember that concept from the past, but it's no longer accurate. We wouldn't consider it true. It can be a confusing term, which is why you won't see it show up in textbooks anymore.